8P120, Chapter 2. Topics here, molecules and chemical reactions. Molecules and compounds. Well, I already mentioned molecules in the last topic, but it's worth being perfectly clear. A molecule is when there are two or more atoms chemically bound to each other by ionic bonds, such as sodium chloride, or by covalent bonds, such as oxygen. So molecular oxygen, O2, would be a covalent bond, ionic bond between Na, sodium chloride. So two or more atoms bound together by ionic or covalent bonds form a molecule. Now, if that molecule possesses two or more different elements, then it is also called a compound. So for instance, methane, CH4, is a compound as well as a molecule because it has two different elements. Sodium chloride is also a compound because, again, it has two different elements. So many molecules are compounds, but there are also molecules out there that are not compounds, like oxygen. So the molecular formula, what we see written out in letters and numbers, tells us what type of atoms and how many are present in that molecule. So for instance, H2, H is the symbol for hydrogen, so we have two hydrogen atoms in molecular hydrogen. O2, O is for oxygen, so two oxygen atoms in molecular oxygen. H2O, two hydrogen atoms and one oxygen atom in the molecule water. CO2, C for carbon, so we have one carbon and two oxygen atoms forming carbon dioxide molecule. So how many atoms make up the water molecule? How many different elements make up a water molecule? How many hydrogen atoms are in a water molecule? And how many oxygen atoms are in a water molecule? You should be able to answer all these questions by looking at the molecular formula of water. Answers being, of course, three atoms, 1, 2, 3, two different elements, hydrogen, oxygen, two hydrogens because of the little 2 next to the hydrogen, and one oxygen because oxygen is present, and if they don't put a little number after it, that means it's assumed that number is 1. All right, structure formulas are another way to show molecular formulas, but to give an idea of how the atoms are arranged and joined. So molecular hydrogen, one little line here says it's a single covalent bond. Molecular oxygen, two little lines here means it's a double bond. So a covalent bond with double bond, two electrons are being shared. Water can be shown this way. Again, a single bond between each hydrogen and the oxygen, but because it is not distributed evenly, we got the hydrogens and the oxygen forming sort of a V shape. And then carbon dioxide, carbon has two double bonds, one for double bond per oxygen, and this ends up being a very linear molecule. Here is a much more complicated molecule shown in structure formula. This molecule is made up only of carbons and hydrogens, and so they just each point is a carbon, and we assume the hydrogens are present, and the extra line would be a double bond. And what's cool is they've actually been able to look at this molecule using pretty advanced microscopy, and it actually does look kind of like the structural formula. Pretty amazing there. All right, chemical reactions. Chemical reactions are when you have starting materials that then turn into new ending materials. And there are gazillions of chemical reactions that occur in the human body, and we'll be talking about chemical reactions throughout the semester. So, in a chemical reaction, you start with certain molecules. So here we have molecular hydrogen, molecular oxygen, and then the chemical reaction occurs and you end with a new molecule, in this case, water. The big 2 in front of the molecule tells you how many of those molecules are needed for the chemical reaction. We refer to what you start with as substrates or reactants. Sometimes they're called substrates, sometimes they're called reactants. So hydrogen and oxygen are the substrates. And then what you end with is referred to as the products. So water is the product. And the arrow That is the direction of the reaction. The arrow lets you know that you're going from substrates to products. So when you see the arrow is always pointing to the products. The arrow is always pointing to products. Remember, you see a chemical reaction, you see the arrow. What is it pointing at? It's pointing at the products. So that means these have to be the substrates. These are the products because the arrow is pointing to the products. Really, this is important. There will be many, many questions asking you which of these things in the chemical reaction is a substrate, which of the things in the chemical reaction is a product. And if you can't remember what's the substrate and what's the product, you will get those questions wrong. All right, so in this chemical reaction, how many hydrogen molecules are found in this chemical reaction? You should be able to tell that by looking at this chemical reaction. How many hydrogen atoms are in the substrates? And how many hydrogen atoms are in the products? Give you a second to think about it. So there are two hydrogen molecules. The big 2 next to the H little 2 means there are two hydrogen molecules. Each hydrogen molecule is made up of two hydrogens. So how many hydrogen atoms are in the substrates? Well, you take the big 2, multiply it by the little 2, that is 4. So there are 4 hydrogen atoms making up the substrates. Then how many hydrogen atoms are in the product? Well, again, you multiply the big 2 by the little 2, and that gives us 4 again. So you'll note that you have the same number of atoms of hydrogen in the substrates as you have in the products. Luckily, we will not be balancing chemical reactions in this course, so we will always be given balanced chemical reactions. I just want you to remember that however many hydrogen atoms on one side will be equal to the number of hydrogen atoms on the other side. The number of oxygen atoms on one side will be equal to the number of oxygen atoms on the other side. All right, so when we do these chemical reactions, we have to break bonds. So we're breaking the covalent bonds between the hydrogen atoms and the hydrogen molecules. We're breaking the covalent double bonds between the oxygen atoms and the oxygen molecules. And then that allows for new bonds to form. So now we have hydrogen bonds to oxygens, new bonds, giving us the water molecules. So chemical bonds have to break and then reform in a new combination during most chemical reactions. Again, we will have the exact same number of atoms of the exact same types on both sides of the chemical reaction. We do not lose or gain atoms. There will be 4 hydrogens here, 4 hydrogens here, 2 oxygens here, 2 oxygens here. There's no loss or gain of atoms from the chemical reaction. All right, there are a few different categories or types of chemical reactions as you would know them via chemistry. First up is synthesis reactions. In a synthesis chemical reaction, you have 2 or more atoms or molecules being joined together to make something new and bigger. So the generic formula would be A plus B yields AB. So again, with the hydrogen and oxygens, we have A hydrogens, B oxygens, and they yield AB water, which has both hydrogens and oxygens. So synthesis, smaller things getting joined together to form a bigger thing, synthesizing water. Then there are decomposition reactions. Decomposition reactions are where you take larger molecules and break them into smaller ones. So basically going from large to small. So the generic chemical reaction would be AB yields A plus B. So here we have mercury oxide molecules, and they will break down, decompose into mercury atoms and oxygen molecules. So again, AB becoming A and B. Then we have exchange reactions. Exchange reactions are where you have 2 molecules, at least, at a minimum, and they switch parts of the atoms between the molecules. So generic formula AB plus CD yields AD plus CB. See, parts switch to each other. So for instance, hydrochloric acid plus sodium hydroxide yields sodium chloride and water. So the Cl switched over to the Na, giving us sodium chloride, and the H bound up with the OH, giving us water. Exchange reaction. All right, here are some chemical reactions. I'll take a moment, pause the video, and determine which of these are synthesis reactions, which of these are decomposition reactions, and which of these are exchange reactions. So again, take a moment to do this. All right, since you can pause the video, I'm moving on. All right, so what do we see? We see that the first chemical reaction is a decomposition. The molecule is breaking down into its subtypes. The second is an exchange reaction. We see the OH moving to the iron, the chlorines moving over to the ammonium. Third one, oxygen plus chlorine yields hydrochloric acid. That is a synthesis reaction. D, the fourth one, is another synthesis reaction. EE is another decomposition reaction where the ammonium is breaking down into nitrogen and hydrogens. And then finally, F is an exchange reaction. Part of one is being switched over to the other. I know it isn't a double exchange, it's just a single exchange, but still important to know. All right, and what are these arrows pointing to? What do the arrows point to? In a chemical reaction, what do arrows point to? The answer is product. The arrow points to the products. So you know what the products are because the arrow is pointing to them. Please learn that. All right, some chemical reactions are reversible. That means they can go in either direction. So they're shown by a double arrow, maybe one arrow pointing one way, one arrow pointing the other. This means that either side can be the reactants, either side can be the products. We see this occurring in biology a lot, so it's important to know that some chemical reactions can be reversible, can go in either direction. All right, now chemical reactions occur at a certain speed, a certain rate, and this depends on a lot of things, including temperature and concentration and so on. But in our bodies, we need those chemical reactions to occur really quickly. So most, not all, but most chemical reactions that occur in the human body needs a catalyst to speed up that chemical reaction. And catalysts speed up the chemical reaction, make it occur faster, and in the process of doing that are not used up. So those catalysts are going to still be available to speed up other chemical reactions, increase the reaction rate. So basically this is talked about in the idea of activation energy. So you have your reactants, you have your products. The reactants have to overcome this mountain of activation energy before they can become the products. And so that will make the chemical reaction extremely slow. However, you add catalysts. Catalysts will lower the activation energy, and this will allow the reactants to become the products much, much faster. So by the catalysts lowering the activation energy, they speed up the chemical reaction, they increase the rate of the reaction. And there are many things that can be catalysts in the human body. The most common type of catalyst is enzymes. Enzymes are proteins. Enzymes are produced by our body. Enzymes are catalysts that will speed up specific chemical reaction. We need them to be able to function. And that is it for this part of the lecture.